So students, now we will see the expressions of work done in both isothermal and adiabatic processes. It means both in case of isothermal expansion and isothermal compression, and in case of adiabatic process, both in adiabatic expansion and adiabatic compression. Now, so let's get first started with work done in isothermal process. Now, since the process is isothermal, so obviously we have already learned the temperature will remain constant. Temperature is not going to be changed. So suppose at any constant temperature, if the change in volume of any gas, of certain amount of gas is if dV, then we have already learned that the work done by gas, that is external work done by gas, is dW is equal to pdV. So suppose for a gas of pressure P and at absolute temperature T, the external work done by gas W is equal to, from integration V1 to V2 dW, where V1 is the initial volume and V2 is the final volume. We don't know nothing about whether it is going to be expansion or compression. Initially we are not taking any particular process. It is thus the process, okay, where the initial volume is V1, then final volume is V2, this change volume V2. So now using the equation PV is equal to N at T, that is ideal gas equation. Now here we have assumed for 1 mole of gas, PV is equal to N at T, N is equal to 1, R into P. R is the universal gas constant, T is the absolute constant temperature. Okay, so we will learn more about it in detail in the chapter ideal gas equation. So now is PdV, we have already learned, that is work done by gas externally, or external work done by gas is dW is equal to pdV. So now putting the value of P from here, the PV is equal to RT, so RT by V into dV. Since both R and T are constant, so it will take out as a constant outside. Then V1 by V2, from V1 to V2 dV by V, by integrating RT ln V2 by V1, RT ln V2 by V1. Base is to the base E, or we may write in the form of logarithm, that is RT log V2 by V1 to the base 10. Now in case of isothermal process, from Boyle's law, since temperature is constant, so PV is equal to constant, so P1 V1 is equal to P2, P2 equals to P3 V3. Okay, so since there are two values, that is V1 to V2, so we don't need P3 V3, so P1 V1 is equal to P2 V2. From here we can easily write V2 by V1 is equal to P1 by P2, since volume and pressure are inversely proportional to each other. So now the final expression of work done in this process, that is W is equal to RT ln V2 by V1 is equal to RT ln P1 by P2, or log V2 by V1 log P1 by P2 to the base 10. Not a big issue. Now discuss about what will be the work done in case of both expansion and compression. So in expansion, we have already learned when gas expands, its volume increases, and which is called work done by the gas, and we have already discussed about that. It is positive. Why it is positive? Let's see. In isothermal expansion, final volume is more than that of initial volume, since it expands, or we can say initial pressure is greater than final pressure. So this expression V2 by V1 or P1 by P2 is obviously greater than 1. So it means work done is positive. This is called work done by gas. Okay. Previously we have learned theoretically, now here we have learned mathematically. In case of compression means volume decreases. So obviously V2 is less than V1 or P1 is less than P2. So we may write the value of this fraction V2 by V1 or P1 by P2 is less than 1, means negative, which is called work done on the gas. Okay. Let's move on to the work done in the next process, that is adiabatic process. Okay. Now in this case, since temperature is not constant, so it will not follow or obey Boyle's law. So let's see now. Expression for work done by the gas is same, that is W is equal to from V1 to V2 pdV. Now instead of Boyle's law, it will follow Poisson's law, okay, which I just forgot to mention in the previous video, that is PV to the power gamma is equal to constant, where gamma is the ratio of the two specific heat of the gas, that is at constant pressure and constant volume, which we are going to discuss in next video. So putting the value of P from here, that is A divided by B to the power gamma means B to the power minus gamma dV. K is constant, taking out integration, you know, x to the power n plus 1 by n plus 1. So minus gamma plus 1 means 1 minus gamma, 1 minus gamma. 1 minus gamma at the denominator V2 by V1. So V2 by 1 to the power minus 1 minus V1. Up to this, okay. Now it is reversed, gamma minus 1. It means you are taking a minus common from here, isn't it? Like this, isn't it? So, isn't it? 1 minus gamma, initially it was 1 minus gamma. So if you take minus, it will be minus gamma minus 1, just like this. 1 minus gamma, if you take minus common, you have gamma minus 1. Minus gamma minus 1 is plus. So exactly, there is 1 minus here. Now again we have again we have taken 1 minus, isn't it, minus V2 into 1 minus gamma. Look at it. So this minus and this minus cancels, lower minus and upper minus cancels, so it turns into gamma minus 1 into V1 to the power gamma minus 1, okay, V1 to the power 1 minus gamma minus V2 to the power 1 minus gamma. Then again after this we have changed this V1 into 1 minus gamma, again we have taken 1 minus gamma, V1 into minus gamma minus 1. So minus gamma minus 1 means 1 divided by x to the power minus n means 1 by x to the power n, just reverse. So V1 to the power gamma minus 1 minus 1 by V2 to the power gamma minus 1, just reverse, isn't it? Here it is V1 and here it is V2, isn't it? Minus gamma minus 1, like this. So 1 by gamma minus 1, when k is multiplied, k is just multiplied with both the fractions. Now 1 by gamma minus 1. Now since it follows the equation Poisson, so we can write P1 to the power gamma is equal to P2 to the power gamma is equal to k. Now instead of k, we have just put the value P1 to the power gamma minus P2 to the power gamma. You can see from here. Okay. Now 1 by gamma minus 1. Now here V1 to the power gamma minus 1 means by V1, so V1 will be multiplied in the numerator. So V1 to the power gamma, V1 to the power gamma cancel, V2 to the power gamma, V2 to the power gamma cancel. So we have P1 to the power minus P2 to the power. Okay. Now for 1 mole of gas, again we will use the formula P is equal to N at T, here N is equal to 1. For N mole of gas, we can easily put the value of N small. Okay, but for easier, okay, but for our convenience, we have just taken 1 mole of gas. If you take N mole of gas instead of N, here it will be letter N. P is equal to N at T, small n at T, doesn't matter. Here we have taken 1 mole of gas. This is the expression in absence of the N. If we assume N mole of gas, there will be the expression N will be added in this expression, doesn't matter. So P1 V1 to P2 V2 is equal to RT, clear. So P is equal to RT, so P1 V1 is equal to P2 V2, so R is equal to constant, so taking, okay, RT1 in case of P is equal to RT, so in case of P1 V1 is equal to RT1, P2 V2 is equal to RT2, because R is universal gas constant. R taking out P1 V1 P1 minus P2. Now in case of adiabatic process, it means adiabatic expansion. In adiabatic expansion, what happens? Since finite temperature, it means in case of adiabatic expansion, what happens? As we have already done, the gas generally becomes cooled down, the temperature reduces, the internal energy decreases, so it means temperature decreases, so it means final temperature is less, initial temperature is higher, cool down. So T2 is less than T1, okay, T2 is less than T1, so it means this expression, T1 is greater than T2 means it has positive value, so this is called positive. This is again, it is called work done by the gas. Okay, that's why it is called positive. Okay. Again, in case of compression, what happens? Final temperature increases. That is T2 greater than T1, isn't it? So this has a negative value. So it means work done is negative, isn't it? Which is called work done on the gas. Clear? So this is the mathematical expression of work done in case of isothermal process and in case of adiabatic process.